lecture meant to make up for the lecture that was canceled on Friday, March 13th, 2020. I suspect that our class, at least, which has 72 people, will maybe be banned from meeting for the rest of the semester, so there may be a lot more lectures like this. If so, I hope these kinds of lectures work. Last time, we talked about the fact that there is a convenient and useful set of standard equations of state, which include equations of state for volume and pressure, equations of state for energy and temperature, but especially for the moment, we're focused on the equation of state for chemical potential. And the key thing about that, the thing that makes it adaptable to many different situations, is this idea of activity. The activity varies depending on what kind of system we have, what kind of chemical component we're talking about. So for gases, the pressure is the key variable that determines activity. For solutes, for any phase that's essentially pure with only minor impurities or minor solutes dissolved in it, then the mole fraction is appropriate. Also for any ideal solution, so mixtures of very similar liquids, for example, the mole fraction is the appropriate measure of activity for in all concentrations, even when the solute may be in fairly high concentration. Then the most common case is when you have a dilute solute, usually a solid mixed with or dissolved in some other solute, and then the concentration of the solute itself, rather than the solvent, is usually given by molar concentration. Occasionally, you'll see mole concentration used. Our book, in fact, tends to use it even in situations where I haven't seen it used before. I don't know if there's any situation, however, where mole concentration is actually required. In all the situations I know of where mole concentration is used, molar concentration would actually work at least slightly better. So in all of my notes, I'll be using molar concentration exclusively. I don't know of any situation where mole concentration is really preferable. It's in the books for historical reasons and traditional reasons rather than for accuracy or theoretically justified reasons. All right, we also then talked about the fact that for an awful lot of cases, it's possible to derive the conditions of equilibrium and all kinds of useful rules by thinking of the case as a chemical reaction. So for Raoult's law, we think of there being an equilibrium between, say, substance A in the liquid and vapor phase. We think of it as being a reaction. A in the solution phase or in the mixture phase goes to A in the vapor phase, and from that we can write down immediately the Gibbs free energy change for that reaction, that thing we're thinking of as a reaction, and then the Q for that free energy is the Q you would get by looking at the chemical reaction itself. Also, the standard Gibbs free energy change is the standard Gibbs free energy change for the reaction in question. So Raoult's law can be derived using that idea. Here is Raoult's law. It's just a few steps away from the reaction idea. And also situations where, for example, you're looking at the equilibrium between a solvent vapor and that same solvent in the liquid phase in the presence of some impurity or another. You can derive another version of Raoult's law using the reaction idea. It also applies to Henry's law. I don't think I talked about this last time. But if you have, in this case, a gas in the gas phase above a solution, and that gas is dissolving or is in equilibrium with dissolved gas in the solution phase, or alternatively, if you have some solute, whether it's a gas or not, and there's an appreciable vapor pressure for that solute in the vapor phase, both of those are really the same case. If the solute is a dissolved solid, then this vapor pressure is probably not very high, but it's probably not zero either. And so in either case, where you've got a gas that's dissolving, where you think of it as a gas dissolving in a liquid, or a solute evaporating into the vapor phase, then the chemical reaction is that something in the gas phase goes to something in the solution phase, or vice versa. And you can write down an equation for the Gibbs free energy change for that reaction. You can derive conditions of equilibrium for that reaction. You can derive an equilibrium constant for that reaction. And yeah, here's K, a Henry's law constant in effect, and derive an expression for the relationship between the concentration of the dissolved species and the pressure of that same species in the vapor phase. The relationship has this constant that can be called a Henry's law constant. There are a variety of different Henry's law constants. So in this case, we're defining the Henry's law constant as a relationship between molar concentration and pressure in bar units. But the book, for example, defines the same kind of thing in a slightly different way. They describe the Henry's law constant as being a relationship between the mole fraction of material in the dissolved phase and the pressure in bar units, usually in the vapor phase. The idea is the same. There's some relationship between these two different kinds of constants. You can derive it if you want. You'll see different constants listed in different tables depending on which source you're looking at, but the idea is essentially the same. All right, I also mentioned that there's a whole bunch of other possible cases. You can have a solid as effectively your solute. There can be a gas in the vapor phase and a dissolved solute in the solid. Same kind of relationships prevail or apply. The delta G will be different because now you've got a solid acting as the solute rather than a liquid. But apart from the fact that the value will actually be different, it's the same idea. You'll get the same kinds of relationships. Likewise, if you're talking about a solid dissolving into a solvent, then the chemical reaction in question, I don't think I wrote it down in this case, well, here it is A in the solid phase going to A in the dissolved phase. The activity for the solid is the mole fraction of solid material of A in that solid phase. If the solid is pure, as it usually is, or very close, then that's 1. And so the activity just doesn't even show up in that case. It's a pure constant. The activity in the dissolved phase is the molar concentration for A in that phase. That means Q is then the molar concentration divided by the standard state molar concentration divided by the activity for the solid, which is a 1 in this case. The delta G is the delta G for the dissolving process, which can be found in tables. And setting delta G equal to 0 to find the equilibrium conditions, you find that the equilibrium concentration for the dissolved solid over here is an equilibrium constant, and now because there's no other concentration variable involved, it's just purely equal to the equilibrium constant, which in this case is called a KSP, or a K solubility product. If it's a slightly more complicated solid, one that dissociates in solution like most ionic solids do, then the activity for the solid is still 1 if it's pure. The activity for one of the ions, magnesium 2 plus in this case, is the magnesium 2 plus concentration divided by the standard state concentration. The activity for the chloride is the molar chloride concentration over the standard state concentration, usually 1 molar, almost always 1 molar. We can write delta G equals delta G0 plus RT log Q. In this case, Q is equal to the activity for magnesium 2 plus, which is proportional at least to the magnesium molar concentration, the activity for chloride ion concentration squared, right? Because there's a 2 chlorides are produced every time a magnesium chloride molecule dissolves. And then all of those are divided by, in each case, by the standard state concentration, and since there's 3 powers of it in this case, you get standard state concentration cubed. And if you set that this delta G expression equal to 0 and solve for the equilibrium expression, you get the standard, you get the KSP expression that you've all seen from freshman chemistry earlier, where now the equilibrium constant is related to the delta G for dissolving of the ionic liquid in this case. Now, let me say something about this case. Whenever ions are involved, the activity really should have an activity coefficient. That's the whole topic of Chapter 10, and we'll talk about that at length in not very long from now. But for the moment, let's ignore the activity coefficients, and so this expression becomes okay. In freshman chemistry, that's the expression you used. In this class, we'll try to do better than that, but for the moment, we'll just go with it. All right, likewise, if you have some impurity that's common to 2 different phases, so here you've got an oily phase and an aqueous phase, and some molecule X that dissolves in both of them, but dissolves to a different extent in both of them probably, then there's something called a partition coefficient that controls how much, at equilibrium, how much X is in the hexane phase, how much X is in the water phase. You know, if it's something that's quite hydrophobic, it'll mostly dissolve in the hexane phase, in the more hydrophobic phase, in the more gasoline-like phase. If it's something that's quite hydrophilic, like an alcohol, for example, then it'll mostly dissolve in the water phase. But that depends on the molecule, depends on what X is. Our chemical reaction in this case is, say, if we're thinking of the reaction as going this way as forward and backwards as reverse, then it's a molecule in the hexane phase going to a molecule in the water phase. It doesn't matter which way you consider to be forward. It just will change the sign of this delta G of transfer, and everything will turn out right as long as you're consistent in keeping the reaction as written straight. But we'll go with this way of thinking of going from hexane to water as the forward reaction for the moment. All right, in that case, the activity in the hexane phase is the concentration in the hexane phase, again divided by standard state concentration. The activity in the water phase is also molar concentration, since it's a dilute solute in both phases. The delta G expression is delta G equals delta G for transfer, right? So it's the delta G, it's the free energy change when a molecule of hexane transfers from the, when a molecule of X in the hexane phase transfers from the hexane phase to the water phase. That's the delta G that we need in this case. And the Q is the ratio of the activities, activity for the hexane phase, activity for the water phase divided by activity for the hexane phase. And since the standard state concentrations divide out now, that just becomes the molar concentration in the water phase divided by the molar concentration in the hexane phase. setting that equal to 0 and solving gives you that the ratio of the two concentrations is equal to a partition coefficient. That's the partition coefficient I mentioned a minute ago. And we can see now that that's just an equilibrium constant. It's just E to the delta G for transfer from hexane to water divided by RT. And so if you know this delta G, you can calculate the partition coefficient. If you know the partition coefficient and the temperature, you can calculate the delta G. And making measurements at equilibrium is one way to find the partition coefficient experimentally, and therefore a way of experimentally also finding out what this delta G of transfer is. All right, so those are some examples of using this idea of a chemical reaction to very quickly derive all kinds of rules for special cases. Here's a couple more of them. One of them is not obviously a chemical reaction to begin with, but it's still, the formalism still works for this case. Let's suppose I have some sodium that's inside, let's say, a cell wall or cell membrane, and it's possible to get out through a channel and go to the outside phase. That we can consider to be a chemical reaction. Sodium on the inside goes to sodium on the outside. That can be written as a chemical reaction. The activity on the inside would be the molar concentration on the inside divided by standard state. The activity on the outside is again the molar concentration on the outside. We can write our delta G for that reaction, our delta G relationship for that reaction. But in this case, there's no standard state delta G, right? Because nothing has changed in going from the inside to the outside. That's what's special or weird about this case. There is no change in the delta G in going from inside to outside. So the delta G in this case is just 0. Delta G 0 is 0. And delta G overall, the full delta G, is just equal to RT times the log of the ratio of the inside and outside concentrations. And so you can calculate what the driving force is. If I've got a high concentration in here, for example, and a low concentration out here, then this would be high, a big number. That would be low. That ratio would be less than 1. The log of that will be negative, and that means the delta G is negative, which means that there's a driving force, a net driving force for moving from the high concentration region to the low concentration region. We'll see that in a more important example in Chapter 11 when we talk about electrochemistry. This will generate an electrochemical force, in fact, in this case. But for the moment, we just note that anytime there's any kind of concentration difference between two regions of space, then there will be a delta G, a driving force, that tries to even out those concentration gradients. If the concentration gradients ever do reach equality, so that the concentration on the outside is equal to the concentration on the inside, then of course this ratio will be 1, and in that case delta G will be 0, as you would expect. Here's the case from the exam that I think lots of people found difficult. In this case, you have two regions of space, both of which have air in them. One is at low altitude. The other one is at high altitude. And we're considering the transfer of some quantity of air between those two regions to be a chemical reaction in which air is transferred, right? Air low goes to air high. That can be also written as a chemical reaction. Since it's gases in both cases, we write the activities to be the pressure in the low case divided by standard state pressure, and for the high activity, pressure in the high box or in the high region. Writing delta G expression, our driving force, our chemical driving force, then there's a delta G 0 for that, and plus RT log Q, and Q in this case is just the ratio of the pressures between the high region and the low region. delta G in this case, remember that any free energy change is the work that you did in order to bring about that change. And in this case, the work that you do is gravitational work. There's a gravitational force that's equal to mg acting on the air as you move it from below to above. And therefore, the work that you do is the force times the distance, so mg times the height difference between the two sides. And that work will then be our delta G0. So I didn't write it here, but delta G is then equal to mgh plus RT log of P high over P low. And now, setting that equal to 0 and solving for the condition for equilibrium gives us that the ratio of pressures, the pressure difference between the high region and the low region, is equal to, as always, e to the minus delta G for that transfer over RT, which in this case is e to the minus mgh over RT. I won't go through it in detail because it's on the exam, and you guys presumably have all tried at least to plug numbers into that expression. But in fact, it gives quite reasonable results. I don't know if the pressure difference in Albuquerque is really due to gravitational work, but in fact, the pressure in Albuquerque is only about 0.85 atmospheres usually relative to sea level. And that's the number you get from this calculation for either nitrogen or oxygen, pretty close. And so I think there are other factors that also control pressure differences, and in fact pressure differences vary from moment to moment, from day to day, in any place on Earth, and Albuquerque included. But on average, I wouldn't be surprised if the gravitational work that's required to raise air from sea level up to Albuquerque level is the origin, the main origin, the main contributing factor in rather low pressure in Albuquerque, and of course even lower pressure on the tops of high mountains like Mount Everest. All right, so that is all that I'm going to cover for Chapter 9, mainly. There is a bunch of stuff in Chapter 9 on various binary phase diagrams of various sorts. They're quite complicated. In the interest of time, I'm going to not lecture on that material, however. If that material is important to you, come and talk to me, and I'll consider putting it into later lectures, but for the moment I think it's less important for most students, and I'd like to get on to other material, especially the stat mech section is coming up, and I want to leave as much room as possible and much time as possible for that. All right, next topic, osmotic pressure. So in this case, we have a fairly unusual setup, not that unusual. Lots of living things have situations where osmotic pressure applies, but unusual compared to the kinds of things we've considered before. The key part of the whole of an osmotic situation where osmotic pressure is relevant is a semi-permeable membrane. Semi-permeable means that some things can pass the membrane, so usually the solvent, and usually the solvent is water. Usually the solvent can pass the membrane, but there's some sort of impurity on the other side of the membrane that can't get through the membrane, and oftentimes it's because the impurity is either charged or very large. It's a large molecule like a protein. Charged molecules can be prevented from getting through a membrane by countercharges that are on the membrane itself. They just repel a charged molecule, or by the fact that the pores in the membrane are just too small for a big molecule to get through. So whatever the mechanism is, there exist things called semi-permeable membranes, and they prevent certain kinds of impurities from passing through. What that means is that the concentration of impurity on one side can be completely different than the concentration of impurity on the other side. The presence of the concentration of impurity on the impure side actually lowers the chemical potential of the solvent on the impure side. So the chemical potential of the solvent on the pure side is actually higher than the chemical potential of the solvent on the impure side. So at equilibrium, in a situation like this, the chemical potential on side A, so it's all solvent here. It's not two different materials, it's solvent on both sides. But solvent on side A chemical potential has to equal the chemical potential on side B. And that means that in order to achieve equilibrium, something has to be done to overcome the fact that the solvent has lower chemical potential on side B due to the impurity. And the thing that causes things to become equal is that as solvent moves through the semi-permeable membrane from side A to side B, the height, in this case, of the solvent on side B rises. That causes there to be extra pressure due to the weight of the water on side B. The pressure on side B is actually higher than the pressure is on side A. That causes a difference, a change in the chemical potential on side B that counteracts and eventually raises the chemical potential on side B up to equality with the chemical potential on side A. And the height difference on the two sides is a measure or a consequence of that pressure difference. Okay, so what we need to do then is look again at our expressions for chemical potential, now accounting for the fact that the pressures aren't the same on the two sides. On side B, the chemical potential will be the standard state chemical potential at the high pressure, pressure B, plus the term that accounts for the impurity. In this case, because we're looking at the solvent on side B, our activity is going to just be, we're going to ignore equal activity coefficients, so the activity will just be the mole fraction of the solvent, not of the impurity, the mole fraction of the solvent, because it's the solvent chemical potential we're looking at here. That's the mole fraction that appears. On side A, the pure material, there's no impurity, so there's no RT log anything over here. And it's just the standard state chemical potential that matters at whatever pressure happens to be relevant, right? So it's the pressure on side A on this for the solvent on side A, and it's the pressure on side B for the solvent on side B. Because the two are not the same, these two standard state chemical potentials are not the same, and so we have to derive an expression for what difference there is between these two guys, and that's what I'm doing down here. We know that a small change in chemical potential using the usual Gibbs free energy trick is equal to the molar entropy times dt, but there is no temperature difference in this case, plus the molar volume for either side A or side B, times the pressure, any small pressure difference for that same side. If we integrate both sides, that gives us that the difference in chemical potential caused by a pressure difference is just equal to the molar volume for the phase in question times the pressure difference caused between the two sides. So if we say that this is the standard state potential for pure A, and this is the standard state potential for the impure A, for the side with the impurity, then this is the pressure difference between the two sides. This is delta P, and we call that the osmotic pressure and give it a special symbol. We call it pi. The Greek P, the Greek letter for P, you could call it delta P as well, and sometimes it is called delta P, but it is fairly standard to call the osmotic pressure difference by this Greek letter pi. Sometimes it's a capital pi. Your book likes to use a lowercase pi, so I'll use a lowercase pi too. All right, that means that the standard state pressure on side B is the same thing as the standard state pressure on side A, plus this pressure difference term that depends on the molar volume for the molar volume for the pure solvent, usually water, times the pressure difference, the osmotic pressure difference. So putting all that together, and equating the two chemical potentials, actually that's wrong. It's not the standard state chemical potential, it's the total chemical potential. We get that the chemical potential on side B is this, chemical potential on side A is that. That standard state chemical potential at pressure A is now the same as that standard state chemical potential at pressure A. There's the difference term. And we get, after solving, so there's 0 on this side, this stuff on this side. If we solve now for the pressure difference that applies, we get that the osmotic pressure is equal to RT times the logarithm of the mole fraction for the solvent, remember, not for the solute, divided by the molar volume for the solvent, for the pure solvent. This is the most accurate expression. Okay. But it's not the most convenient. So it is traditional to do a little bit more work to get a more convenient form, and we'll do that in a minute, but yes, I guess I have this point that I forgot to make. Let me make it now. This expression doesn't depend in any way on what the impurity is, and so all that matters is this mole fraction for the solvent, not the mole fraction for the impurity. And what that's accounting for is, indirectly anyway, is the freedom of translational entropy that's available for the solute, for the impurity itself. And so the osmotic pressure effect, the fact that there is a pressure difference between the two sides, is purely due to the translational entropy that's available to the impurity, to the solute, and due to the fact that when solvent transfers from the pure side over to the impure side, we're giving more volume for that impurity to run around in, more translational entropy for the impurity than it would have had beforehand. And so the pressure difference ultimately is caused by a pure entropic translational entropy effect that doesn't depend on, it depends on how many particles there are of what the concentration is, I guess, if you like, of the impurity, how many impurity particles there are, but not on the chemical identity of the impurity. All right, I'll come back to this in a minute. This is calculating the pressure difference caused by the height. So if you actually experimentally measure the height, you can calculate what that osmotic pressure difference is, and that's useful. Let's go back on to the approximation. This log of the mole fraction for the solvent is equal to the log of 1 minus the mole fraction for the solute now, for the impurity. And if this mole fraction for the impurity is quite small, as it often is, less than about 0.1, probably oftentimes it's 0.01, then you can approximate this log of 1 minus something as just minus the something itself. Again, that only applies for small impurity concentration. Then you can say that that mole fraction is equal to the number of moles of impurity divided by the number of moles of solvent plus the number of moles of impurity. If the number of moles of impurity is small, as it almost always is, that's approximately moles of impurity over moles of solvent. And now we plug that into all of that stuff into our earlier formula for the osmotic pressure, and doing a little bit of algebra and some identifying of the fact that this quantity, for example, the molar volume of take that back. This quantity is just the solvent volume, right? The number of moles of solvent times the molar volume for the solvent is the volume of the solvent. And dividing the number of moles of solute is just the molar, it's moles per liter, so it's just the molar concentration of the solute. And so you end up with this nice compact formula. The osmotic pressure is equal to RT times the molar concentration of the solute now, of the impurity now. Notice that that's exactly the same formula as for an ideal gas. It's a completely different physical situation, and yet you get exactly the same formula as you would for an ideal gas, which makes it easy to remember. It doesn't really change anything else, but it does make it easy to remember how to calculate osmotic pressure. Here's an example. Let's suppose I have a 0.1 molar solution of impurity. And I don't say what the impurity is because it doesn't matter what the impurity is. I do need to know the temperature, so let's say we're at 300 K. Then the only complication is that I got to make sure the units work. In order to do that, I should plug in a value for the gas constant that's in liter atmosphere units, so that I get atmospheres out on this side, and I get and I can use molar concentration for C. It's possible to use the joule unit term value for R, but then you're going to get pascals out over here, and you got to put in moles per cubic meter for the concentration here, and those aren't usually the most convenient units. So using the gas constant in liter atmospheres per mole degree Kelvin, multiplying by 0.1 for our molar concentration, you get a 2.46 atmosphere pressure difference between the two sides in the osmotic pressure situation. And that's for a relatively low concentration. A 10th molar concentration of impurity it can be a lot higher, right? So this is not a particularly high concentration, and yet you get 2.5 atmospheres of overpressure. And the lesson is that osmotic pressure can be large for modest concentration differences between the two sides. All right, going back up here now, I tell you that the pressure difference between the two sides, pi, is equal to the height difference times the acceleration due to gravity times the density of the solvent in question. That makes sense, right? Because the net force that this extra stuff on this side is exerting on the rest of solution here is proportional to the mass of that stuff, right? Mass times the acceleration due to gravity would be the force, and force over area is pressure. And all right, there's a few extra steps in there, but it makes it plausible that density times acceleration due to gravity times the height difference gives you the overpressure. And in this case, I want to use it in reverse. I want to say, given that I know the pressure difference, how high is this height difference? Especially, for example, if I have a tree, and let's say the sap in the tree has a 0.1 molar concentration of impurities. Again, it doesn't matter what the impurities are. It's a big mixture of stuff, but that's all right. And now I have pure water out here. That's gonna, the tree roots have a semi-permeable membrane in them. And so there's going to be an osmotic pressure difference that will drive sap up into the top of the tree, how high can the tree be before the osmotic pressure difference won't do it anymore? That's what we'd like to know. And so solving for the height in this case, we get that the height of the tree, or the maximum height of the tree, is the pressure difference divided by the density of the solvent divided by the acceleration due to gravity. The density of the solvent is 1.0, let's take it to be pure water, grams per milliliter, or equivalently, it's 1,000 kilograms per cubic meter. And we have to use that SI unit because we're going to use SI units for the acceleration due to gravity. Likewise, we have to convert this atmosphere number, which I'm going to take to be the same as bar, well, no, it's atmospheres, that's right, into pascals. The conversion factor is 101.325 pascals, so now I've got pascals on top. And anyway, doing the arithmetic, that gives me 25.4 meters, or about 75 feet, for the tallest possible tree that can get water up into its upper reaches here, up into its leaves and limbs at the top, purely by osmotic pressure effects. Now, in fact, trees have pumps to do that work too, so trees can be taller than 75 feet. And in fact, it isn't necessarily osmotic pressure that's working even for shorter trees than that. But if there were nothing but osmotic pressure to drive sap up into the tops of the trees, then let's say a 50-foot tree would still do fine. All right. I'm going to stop for the moment, and we'll go to the next lecture before we take on this next topic.